So, so here we are in a position to talk about the last application of the autoencoder, okay, which require, another type of autoencoder called the variational autoencoder, okay. So this was proposed in 2013 by Dedrick Kidman and Max Wheeling, okay, and this one has become one of the most popular type of autoencoder. Okay, why? Okay, because this is very different from all the autoencoders that we have talked about. Okay, this one, okay, there are two important differences. Okay, the first one is they are probabilistic autoencoders. Okay, what do we mean by probabilistic autoencoder? It means that the output are partly determined by chance. So the same input may result in different outputs. Okay, the same input may result in different outputs. But we know, like in the previous autoencoder model, okay, yeah, the same input always give you the same output. Okay, of course, like you may argue, okay, how about denoising autoencoder? Denoising autoencoder, we intentionally inject some noises in random, right? Either Gaussian noise or like randomly switch off noise. But if you don't consider the randomness in those noise, then the same input will still give you the same output, right? Okay, so this is like for the past all type of all the types of autoencoder that we have talked about. Okay, none of them will be considered as like a probabilistic autoencoder. Okay, but the variational autoencoder is a probabilistic autoencoder. Okay, and the second most important reason, this actually is the most important reason why variational autoencoder become so popular is because these variational autoencoders are generative autoencoders. It means that they can be used to generate new instances that look like they were sampled from the training set. So yeah, so in a sense that you can use it to generate a lot of data. Okay, so this is these two properties make the variational autoencoder very similar to RBM, restrict Boltzmann machine, but it's much easier to train. And because we didn't talk about variational restrict Boltzmann machine, so you probably don't need to worry about that. Okay, but you need to understand variational autoencoder. Okay, perform variational Bayesian inference. Okay, which is efficient way to perform approximate Bayesian inference. Which is was discussed in chapter 9. Okay, if you want to know more about variational autoencoder, you can check out chapter 9 material for detail. But again, I don't have time to go back there to talk about this. Okay, let me show you how variational autoencoders work. Okay, so this is a variational autoencoder. Okay, the input goes through several hidden layers. So this is the encoder. Okay, and it will be used to generate mu and sigma. Okay, this mu is an average of this sample of this particular instance, this input instance, and the sigma is the standard deviation for this particular input. Okay, and this mu and the sigma will be used. Okay, so assume this is like a input space. Okay, and then somehow this input space will be converted into a coding space like this. So even the input space may look very different, may look very with a special shape or very biased. Okay, eventually they will be converted into a Gaussian distribution. Okay, Gaussian distribution. Okay, and then remember, so this one will generate a mu and a sigma, right? So mu will be used to determine where that location is in this Gaussian distribution. Okay, and sigma determine like you know, the range, and then you are going to use this mu and the sigma to randomly sample a point from this distribution. Okay, this randomly sampled point, okay, will, you know, be very close to this input instance, but not the same. Okay, because they have the same mu and the same sigma. Okay, you just use this mu and sigma to do the sampling to get you another instance here. Okay, and this one, okay, will be converted back to the original shape. Okay, original. We are going to reconstruct the input. Okay, using this instance. Okay, trying our best to reconstruct it by using this decoder. Okay, so that's the concept of this variational autoencoder. Okay, so so this Gaussian noise, okay, mu plus the Gaussian noise times the sigma, okay, this is like a use for sampling, okay. This part is used for sampling and to get an instance. This instance, as I say, is close to the mu and the sig. That particular instance you get from the input, but not the same, not necessarily the same. Okay, so okay, I think like I already explained what this is. Okay, so we can look at the cost function. Okay, it's composed of two parts. The first is the reconstruction loss. We use all the time. Okay, which pushes the autoencoder to reconstruct the input as close as possible. Okay, and the second part of the cost function is the latent loss, which pushes the autoencoder to have codings that look as though they were sampled from a simple Gaussian distribution. So the second loss function will push this input space into this coding space that is what should I say, like as close as like a Gaussian distribution. Okay, so and we call that coding space, okay, as the latent space. Okay, so end up it's going to look like a cloud of Gaussian points. Okay, so after training a variation autoencoder, okay, you can very easily generate new instances by just sampling a random coding from the Gaussian distribution and decode it, and that's it. Okay, so basically like it's a very easy to use. So far all the applications of the autoencoder that we have seen, okay, all the applications that we have seen for the autoencoder are using encoders, right? Right. Think about that. Okay. Well, the only part that is different from, for example, like dimensionality reduction using encoder, right? And transfer learning, the pre-trained. Remember like the greedy layer-wise pre-training, and eventually we use the encoder part for transfer learning, right? Okay, but the only difference is that, okay, for the denoising autoencoder, we use the whole autoencoder, right? But this is this variational autoencoder, or I probably should say like because when we use it for generative model, the decoder is the part we use the most often. Okay, so this is like a very different from the other ones. Okay, so so variational encoder is latent loss. Okay, this is probably a little bit difficult to explain. Okay, L just means latent loss. Okay, K is like the size of the dimension. Okay, or you can say like a number of instances. Okay, and the sigma I and the mu I are the standard deviation and average of each instances. Okay, I mean, so this is like this construct a variational autoencoder, latent loss. Okay, I will not get into the detail, mathematic detail here, but if you are interested, I mean, in knowing more about this, I mean, you can check out chapter 9 and also perhaps some additional material, okay, for the mathematics behind that, okay. So, so here, okay, so you can, you can have like you can first create like this sampling, basically like a given a particular like mu and standard deviation sigma, okay, we try to get like a new sample, okay, by using this sampling, okay, function, okay, and oh, by the way, probably I should say here, there's like I forgot to mention about this, okay, we use a gamma equal to log sigma square, okay, to replace the sigma, because this will help us to when we train the model, this will actually help us to converge faster. So once you replace log sigma squared by gamma, okay, the original function like this one will become like gamma I, right? And this part will be converted into exponential of gamma I, okay? So the other part remains the same. So that's an interesting, twist. I mean, we call that a trick that we can use for the variational encoding. And here, okay, in this sampling function, we actually make use of that the gamma trick, okay, gamma tweak, okay. So you can see we have a log var that represent like gamma actually, okay. So. And then we create an encoder, okay? Here we are using a functional API, okay? Because the model is not entirely sequential. Why? Because you can see here, for this one, we are outputting we have two outputs, right? We have two outputs. So this one cannot be, created by the sequential API. So you can see that, okay. So first, we assume our coding size is 10, okay. As for like what size of the coding you want to use, okay. Again, this is dependent to like what should I say? Like the complexity of the data that you want to generate, okay. Here, because we are dealing with like fashion MNIST. So fashion MNIST, 10 dimensions should be good enough. Okay. So input is kernel is a chaos layer. Okay. Input is 28 by 28. I mean, this is nothing to be surprised with, right? So and then okay. So we use this input, okay, and flatten it. Okay. So this is the flattened input, and then we use 150 neurons. Okay, activation residue. We get the previous layer as the input, and then we use this one as a Z, and then feed it to like a 100 neuron zero activation. So we have another layer, okay, and then after this, okay, so you see for the same layer, okay, the same layer will be used to create the coding mean. Okay, so this Z, okay, we use a dense layer to create this coding mean, okay, and we also use the same input to create the coding log var, which is gamma. Okay, using the dense layer. Okay, so you can see this part is the part that we cannot use the sequential API. Okay, because obviously we have more than one output. Okay, so coding equal to sampling. Okay, so you put this coding min and the coding log var together, and then you call the sampling. Okay, remember we have this sampling function, defined here. This is also actually this is also a layer. Okay, but this layer, the purpose of this layer is this one, to come up with a sample for the decoder. Okay, and then once we have that, okay, we create a variational encoder. Okay, so here we have one input, but we have output. We have three items: coding min, coding log var, and the codings. Actually, the only one that is useful for the decoder is this codings. These two, okay, are the byproduct, or like are necessary to create the codings. But other than after we create the codings, okay, the previous two items are no longer useful. Okay, so this whole thing is the encoder. Okay, and then okay, we can also create decoder. But now, okay, decoder is much easier. Okay, we could use sequential API if we want. Okay, if we want, because you can see here, okay, the decoder is this part, but this part is it doesn't have a very complicated structure. So we could use the sequential API, but here we still use the functional API. Okay, just to be consistent with the previous one. So here we just get the input from the coding size, okay, which is like 10, and so we get it, and then okay, we use this one as the input for this dense layer, 100 neuron, 0 activation, okay, and then the output will be used for the input of next layer with 100 neuron, 0 activation, and this output will be used, okay, for this 784, okay, neurons activation sigmoid. We still treat each neuron, each output as like a binary binary classification. Okay, so we still use sigmoid. Okay, and then we reshape this to 28 by 28, 2 dimension. Okay, and then okay, the variational decoder. Okay, we put them together. So decoder input, output is output. Okay, that's it. And when we put them together, okay, the variational encoder, okay, input, okay, get an input. The output, the first two parts are not used, even though we know like the first one is the mean, the second one is variance, but we are not going to use them anyway. The only one that is useful is the coding. Okay, so the first two are, well, are just a placeholder. Okay, and then we'll use codings for the input of the variational decoder. Okay, we call it reconstruction. And then, okay, we use these two to create a variational autoencoder. Okay, and the input, I mean, input is input, output is reconstruction. That's it. Okay. So we ignore the first two output. I mean, yeah, I think I already explained. And so finally, we need to add the latent loss and the reconstruction loss. So this is like where we create that latent loss. And so the variational so we add this loss, latent loss, okay, to the loss function. But the one thing I mean you probably want to notice is that, okay, for the reconstruction loss, because this reconstruction loss is like a binary closed entropy, right? And the binary closed entropy is computed for each neuron. Okay, but this latent loss, when we calculate it, this is actually for the whole picture. Okay, so because they mean different things, right? One is for one neuron, the other one is for the whole picture. The whole picture has 28 by 28, this many neurons, right? So in order for them to be the same, to have the same, to represent this for just one neuron, okay, on average. So we have to divide the latent loss by 784. Okay, the reason to divide this one is so that, okay, this latent loss is average, so that, I mean, we put this latent loss on each neuron, okay? So we add this one to the loss, and then, loss is binary closed entropy, and we use RMS prop. This is also special, okay? The previous ones, you can see that, I mean, we use like SGD, but this one we use RMS prop. I mean, why is that? I mean, it just happened that RMS prop works better for this variational autoencoder. You can try different optimizer and see like which one is better, okay, by yourself, okay, and then. Okay, I think I don't need to explain this. I already explained. Okay, so then you can train this variational autoencoder. Okay, again using this training set and using the same training set as the label, and you train it for 50 epochs. Okay, batch size 128. Okay, validation. I mean, again using the same validation as like the label for the validation. Okay. And then, once you are done, okay, so you can use this variational autoencoder to generate images that look like fashion items. So all you need to do is to sample random codings from Gaussian distribution and decode them. So here, okay, for example, codings, okay, you just use tf.random normal, okay, shape, okay, you want to generate 12 like instances, okay, of the coding result, okay, and the code. I mean, so because coding size is 10, right? So you generate 12 of these coding size, instances, okay, and put it in the codings, and then you use the variational decoder. Here, see, as I said, we use the decoder for as a generative model. Okay, so this is important. After we train this variational autoencoder, the decoder is the one that we actually use. So we call it, we put the codings there, and then the result, okay, will be put into images. And then if you draw these images, okay, the figure is going to look like this. Not exactly, for example, you can see some pictures are still blurred, right? The pictures are still blurred. This one this looks like a purse. It looks like a purse, but it's not very clear, right? But at least you can see that this represents like a fashion items without any problem, right? You can observe that these are fashion items. Okay, so this is like but these fashion items are generated from random numbers. Okay, we are not reconstructing this from the data set. We are using these randomly generated numbers to generate these pictures. Okay. And the one thing even more interesting, okay, is that we can do what we call semantic interpolation. What is semantic interpolation? Okay, Yeah, it's yeah, we still have time. Yeah, the semantic segmentation is okay. Instead of interpolating two images at the pixel level, okay. I mean, normally when you do interpolation, okay, for example, you say, oh, we just add up the these two images, pixel by pixel, and then divide by 2, right? What you are going to get is like, well, you can probably see like something from, I mean, some image from here and some image from here stacking up together, right? But that doesn't look good, right? That doesn't look good, okay? So that's like a regular interpolation that we can do. We normally do for images, okay? But what semantic segmentation is like this, okay? Remember, all these 12 items are based on 12 randomly generated coding vectors, right? Right? You know that, right? So you can imagine each of them represent a coding vector. Okay. Now, okay, what we can do is like this. We can, you know, this is a vector, this is a vector. We can add up these two vectors and divide it by 2. So we will still have a vector, but this vector is going to be, you know, somewhere in between these two, right? Two vectors, right? It's going to at the middle of these two vectors. And then we use that vector to generate an instance by using this generative model. Okay? So actually what we can do is here, okay? We actually try to, you know, remember this is 3 by 4, right? 3 by 4. We enlarge it to 5 by 7. We intentionally insert some spaces between the column and the row. So of course, when you insert the space between the column and row, you have some empty space to fill, right? So for those empty space, okay, this TF reshape is going to automatically create the interpolated vector for you. Okay, and then you feed these interpolated codings into the variational decoder, this generative model, and what you are going to get is this one. So you can see this the one with like you know, bounding boxes are the ones that originally in here. This is 3 by 4. And then here, we have this 3 by 4. And in between, okay, those are the, you know, the, we generate the, interpolation. I mean, we use an interpolation of these two vectors to generate this one. And then you have a vector, and then use a generative model to generate this one. So you can see, for example, these two are shoes, right? So the interpolated one is shoes, right? That's meaningful, right? Okay, so for example, what else? Anything else? For example, like clothes. These two, well, this is t-shirt, this is dress, right? So this one, it looks like a short sleeve dress, right? So again, this is like interpolation of these two. I mean, but this is semantic interpolation. This is not like a real pixel by pixel interpolation. Okay? So this is a very interesting thing to create. For example, or like anything else. Let me see. Yeah, these two are shoes. So this is a purse actually, but this one is also shoes. Anything else? Yeah, so the other part, I think, I mean, for example, these two are clothes. I mean, this is dress, this is clothes, and we still get a clothes here. Okay, so you can you can somehow see like if two items are similar in certain property, and you get like a semantic interpolation between these two items, that item will still be like that, will still share the same property. Okay, so I think some of them are, if they are very different, I mean, of course, for example, like these shoes and clothes, then the semantic interpolation between these two will not be able to guarantee what it is. In this case, it's probably shoes, but it's not very clear. Or for example, like shoes and the dress. In between, this is pants. So this is very, it doesn't guarantee any special property. But if it's like in between shoes, then this one must be shoes. If it's in between dresses, clothes, then the middle one must be clothes. Okay, that's the semantic interpolation. Okay, just want you to be aware. Okay, that this variational autoencoder, especially the decoder part, can be used as a generative model. I mean, but obviously it does not. The image that this variational autoencoder generates doesn't look so good, right? Okay. Of course, part of the reason is because, okay, yeah, I mean, the model that we have here, okay, it's a relatively simple model. If you want to increase the complexity of the model, yeah, it may perform slightly better, okay, but yeah, the autoencoder still has its limitations. Okay, when you use it to generate the the data set, it's just not that good in terms of quality. Okay, so if you want to really generate some data in good quality, yeah, you have to use GAN, generative adversarial network. Okay, but yeah, I mean, yeah, due to the time limit, we are not able to talk about that. And that's actually like the next topic. But yeah, we only have like 5 minutes left. Okay, less than 5 minutes. So yeah, so that's about it for this semester for the generative adversarial networks. I mean, if you guys are interested, you are more than welcome to check it out yourself. I mean, you can see, I mean, we can actually use it to create like a much realistic result. Okay, for example, not only we can do like, for example, we can use, we can do vector arithmetics for vision. So for example, for example, I mean, these are the codings. If you use their codings, and then, okay, you do an average, then you get, because these three are male, right, with glasses. So you get a male with glasses, okay? And these three are male without glasses, and you do an average for their codings, and you get a male without glasses, okay? And then these three are female without glasses, right? So you do an average of their coding and generate the image. This will be a female without glasses. You can even do arithmetics, okay? Male with glasses minus male without glasses plus female. It becomes female with glasses. Very interesting, right? This is called vector arithmetics. But you cannot probably expect that for variational autoencoder because, I mean, the quality is not that great. Okay, but this one is for like a DC GAN, okay, paper. Okay, so it's very interesting result. Okay, but this is only good for the GAN model. Okay, so I guess that's about it for this class. Any question?
是 GAN 在设计的时候，就是它的结构也会设计的像是
Well, the structure for the gain is very different. Okay, for example, you have like a, here, you have a generator, and you have discriminator. Generator generate fake stuff. Discriminator, you randomly give some fake item generated by the generator, and the real item from the data set. Okay, you randomly give this thing to the discriminator, and the discriminator has to be able to identify it's fake or real. And these two are, each of them will be considered like a complete model, and you train them to fight each other. So this one is kind of like a bad guy. He's trying to create fake stuff. This one is kind of like a police. He's trying to tell the fake from real. And so it's like by competing, having these two models compete each other. So these two models, they are, they will become better and better. Both will become better and better. Okay, but the one that is really useful is this generator. Okay, we are going to use this, to generate some data set. For the GAN. Okay, most of the application for GAN is we use it as a generative model. Yes. Okay. So, but there are a lot of difficulty. To train GAN. Okay. So, obviously I don't have time to talk about those things. Today. But you are more than welcome to check out the second part of this chapter by yourself. If you have any question on that, you are more than welcome to talk to me. Okay, but unfortunately, obviously I cannot. I only have 1 minute. Okay, so any other question? So if no question, remember we have final exam next week, and the final exam, you are allowed to bring in 1-page cheat sheet. I told you guys about that last time, right? Okay, if you don't remember, don't tell me I didn't say that. Okay, so if some student didn't come to here and they didn't know, you can pretend they didn't. They are not your friend. Yeah, just kidding. Yeah, it's up to you. Okay, if they are good friends, you tell them. If they are not, then well. Anyway, any other question? Okay, if no question, I will see you next week. Okay, TA will be here to proctor the exam, but I will be around. Okay? Okay. Thank you. Bye.